Yes, we are. Okay, wonderful. Well, then, welcome everybody. Welcome to the second online seminar in our series Science and Society. So my name is Karen Roelofs. I'm the Vice President of the Association of ERC Grantees. And before we begin, I would like to say a few words about the seminar series and about the format of these events. So the goal of the series is to engage the general public with the fundamental research that is being carried out by ERC grantees, and to highlight the role that bottom-up, investigator-driven scientific research plays in our knowledge-based societies. So over the course of a year, we will organize 4 of such seminars, one each for the 3 core domains, life sciences, social sciences and humanities, and physical sciences and engineering, and one dedicated more specifically to the links between fundamental research and society at large. And today's seminar is dedicated precisely to that question. And to talk about it, we have the great pleasure of welcoming a very special guest, the former president of the ERC, Jean-Pierre Bourguignon. Jean-Pierre will be probably introduced in just a few minutes by Simon Filatreau, but already a very, very warm welcome to you, Jean-Pierre.
Thank you.
We also welcome 3 outstanding panelists, Zoltan Dienes, Véronique Allouin, and Christian Dubrul, and many members of our board here. So, a few points before we begin. So first, this meeting will be recorded and is live streamed to the ERC's YouTube channel, where a digest of the event will remain available later on. To ask questions, please use the Q&A function of Zoom rather than a chat. And don't forget to upvote those questions that you find most interesting. And the most upvoted ones will be put to our speaker when the presentation is over. Please also feel free to say who you are and to comment about the presentation in the chat, but questions in the Q&A, that would be best. So panel members, please don't forget to close your microphones. And I will now hand over to Axel Kleremans, the president of the Association of ERC Grantees. But before I do that, I would like to express our deepest gratitude to the Necker Institute, who is again hosting us today. Thank you, Simon, Fernanda, and finally also we thank Paolo Borghesi and Marcel Monco from the ERC for again arranging the streaming. So very much, thank you very much. And with that I'm done. I see there are already many people actually, 100 exactly at this moment. So let's get going. Axel?
Yes, thank you, Karen. I hope I'm not muted. No, I'm not. So let me join you in extending my warmest welcome to our speaker. I would just like to say a couple of words about the Association of ERC Grantees before we begin. Since our first seminar with Ugur Shahin in early May, we have made substantial progress becoming fully operational and are now literally just a few lines of code away from being able to accept full membership. The board members of our association, a few of them whom you can see here today, are all ERC grantees, which means that we all spend a lot of time thinking about research rather than about how to create an international non-profit organization from scratch. We had to learn how to compose statutes to get them notarized and legally approved, how to convince a bank to let us open an account with them, how to set up an online payment system, and most importantly, how to convince the ERC Scientific Council and board to let us be who we wanted to be. This journey involved meeting dozens of people at the ERC and elsewhere, and we have already achieved a significant presence amongst the organizations that gravitate around the EU in the research and innovation space. Amongst all these people, though, no one played a more important role than Jean-Pierre in the creation of our association. In fact, he initiated it during AERG of 2016 in Manchester, where he put the idea on the table. And what a great idea it was. There are over 10,000 scientists and thinkers of all kinds who benefited from a grant from the ERC. And our dream as the Association of ERC Grantees is to unite them all into a powerful mind bank for Europe, to network them all into a thriving scientific community, and to invite them all into sharing as much as they can about their passion for scientific inquiry with society at large. Thus, we would like to take this occasion to publicly thank you, Jean-Pierre, for your unwavering support during the 3 years or so that it took us to get the association off the ground. And to mark this occasion, even though you yourself are not an ERC grantee, we would like to offer you an honorary membership, or perhaps I should say a patron saint membership into our association, the existence of which owes so much to you. Now, I don't actually have anything to give you over Zoom beyond my most sincere appreciation for you as a person and my utmost admiration for the role you played at the ERC, but perhaps I can show you this and we can all give you a round of applause. If you can unmute yourself.
Thank you very much. Thank you very much.
And with this, I now give the floor to Simon, who will introduce Jean-Pierre properly. Thank you.
Thank you, Axel.
So thank you. It's now my great pleasure to introduce you formally, Jean-Pierre Bourguignon. So to mention your outstanding curriculum, you were president of the European Research Council from 2014 to 2019, and then further acted as interim president from July 2020 to August 2021. Originally a mathematician by training, you spent 40 years of your career as a research fellow at the Centre National de la Recherche Scientifique, CNRS. Your work was mostly dedicated to differential geometry and global analysis at the boundary with theoretical physics. You were professor at École Polytechnique in France from 1986 to 2012, and director of the famous Institut des Hautes Études Scientifiques in France from 1994 to 2013, where 7 professors out of 12 permanent professors were awarded field medals, including 3 during your time as president, as director of this institute, which shows how successful you were at managing a most prestigious scientific institution. You are currently Nicolaas Kuiper professor at the IHÉS, this institute. You have been the president of the Société Mathématique de France and of the European Mathematical Society. For your achievements, you were awarded the prestigious Prix Langevin, Paul Langevin, from Académie des Sciences de Paris, and the Prix du Rayonnement Français in Mathematical Science and Physics. You received numerous honorary doctorates from Keio University in Japan, from Nankai University in China, from the University of Edinburgh, and you are currently the president of the board of the Ludwig Maximilian University, the LMU in Munich. Dear Jean-Pierre, it's truly a special occasion for us, the ERC grantees, to have you speak here today, and we are looking forward to listening to your presentation entitled Highlighting the Scientific Method, Why It Matters. This presentation will be divided into 2 parts with questions in between, and with that, the floor is yours. Please go ahead and thank you again.
Thank you very much, Simon, Axel, and Karin. So it's very nice to see you all, and also to give me the opportunity to speak about this topic about the scientific method. So actually, analyzing the evolution of the scientific method over centuries is an important chapter of epistemology. My purpose today is not to lecture on it per se, but to identify some of its characteristics that connects to the issue I really want to raise in the second part of the webinar, namely why it matters today to make progress on the understanding of the scientific method by various communities. Indeed, many philosophers and scientists, I could list some of them, contributed key turning points regarding the development of the scientific method. Let us start with knowledge. For me, knowledge is a human construction that has been consolidated through the work of many communities stemming from different cultures. In spite of the great diversity of the ways research is conducted today, such a consolidation could happen through the development of a systematic approach coined as the scientific method. Of course, the scientific method has evolved with the broadening and the sophistication of the tools used by researchers. And this process has to be acknowledged. The 5 characteristics of the scientific method I would like to highlight today are: first, the role of the creation of new concepts. Second, what it takes to establish facts. Third, the culture of doubt. Fourth, the value of statistical approaches and simulations. And fifth, taking the time and leaving room for serendipity. I chose them because some of them are somewhat hidden, and actually it's an opportunity to bring them to light. So let me start with the first one. Concerning the importance of the creation of concepts, let me start with one example. The second law of motion, stated by Isaac Newton in 1687 in his Philosophiae Naturalis Principia Mathematica, stipulates that a force applied to a body creates a movement by giving it an acceleration proportional to its mass. The concept of acceleration mentioned there was a key creation of Newton's. At the end of the 17th century, the concept of velocity as variation of distances over time was really about to be mastered. It is not so well known that the Japanese Seki Takakazu was the first to introduce the concept of limit, which is needed to develop the notion of derivative of a function. The names of Newton and Gottfried Wilhelm Leibniz are more often cited to define instantaneous velocity as the limit of the infinitesimal variation of distance over an infinitesimal amount of time. But of course, to get to the infinitesimal variation of the velocity over an infinitesimal amount of time requires a big stretch of imagination, actually an incredible act of creation. Without having such a concept at hand, it is just impossible to come up with a law. Stating this law was a turning point in science, and it had an immense impact in terms of practical applications and engineering, after wrong beliefs on the role of the velocity alone and not the acceleration. It also allowed the complete consolidation of Kepler's heliocentric model of the solar system based on careful observations. This was possible because in his Principia, Newton also proposed a description of the force created by gravitation. In spite of the strong and sometimes brutal resistance by religious authorities, this gave a very solid basis to the heliocentric system, a turning point from the philosophical point of view. Establishing facts requires often very precise measurements delivered by technical tools. In this respect, allowing access to new scales plays a critical role. Over centuries, gaining in precision and accessing both smaller and smaller scales, we are now below the nanometer, that is the billionth of a meter, through more and more sophisticated instruments, microscopes relying on new physical principles, for example, as well as larger and larger ones. It is now become common to speak about light years, that is 10,000 billion kilometers. Using, for example, telescopes gravitating around the Earth have been critical to identify new phenomena and explore new areas. This race for enhanced precision, of course, requires not only sophisticated equipment, but also competent engineers and technicians to build and operate the various operations, the various platforms. They are critical to do good quality work and contribute greatly to the scientific progress. It is in this context that the issue of the proper description and recording of the experimental processes in view of possible future reproduction plays a key role. Experiments need to be very thoroughly documented to make sure that some parasitic effort is not affecting their results. Having access to a new scale requires to decide whether the processes on which the scientific method is based at coarser scales are still adequate or need to be amended. This often goes along with dealing with much more complex phenomena for which an adequate nomenclature has to be established. Again, a process that requires very close collaborations between experts from many different countries and sometimes fields. Of course, many other examples could be given. A very good one is the identification of energy as a central concept in physics, appearing first in diverse disguises, mechanical energy, heat, electricity. It could finally be put under one roof. A remarkable punchline to this quest of unification is Albert Einstein's 1905 formula, E equals mc squared, telling how much energy can be produced when some mass disappears, typically in a nuclear process. Here, c is the speed of light, 300,000 kilometers per second, thus showing the incredible amount of energy such a process frees. Another example, developing a satisfactory description of the diversity of materials one sees in nature has been one of the great adventures of the natural sciences in the last centuries. Antoine Lavoisier was one of the first who dared to suggest that such a classification of elements could exist. And Dmitry Mendeleev, the one who came up with the first so-called periodic table. Confirmation of the atomistic hypothesis and the use of the key concept of quantum mechanics led in the 20th century to the remarkably detailed description of all pure chemical elements available today. This could only be obtained through systematic back and forth movements over 2 centuries, involving many scientists who accumulated experimental data and developed a general architecture given by theoretical constructions. In particular, the new insights into the structure of matter given by quantum mechanics and the role played by electrons. It goes without saying that chemistry goes much beyond pure elements and is interested in complex molecules and processes through which chemical reactions take place, including catalysis, one of the developments being recognized by the Nobel Prize in Chemistry 2021. Science and engineering is now at the point of creating new materials with properties adequate for specific uses. An example is a new form of arrangement of carbon atoms, the so-called graphene. But this affects other areas as pharmacy. The third I wanted to highlight is results can only be considered as scientific if they have survived the scrutiny of experts. This is the basis of the peer review of research articles, a process to which all scientists know they have to submit themselves to be credible. This is why early announcements before the critical stage of the review by experts be taken for what they are, namely only statements.
I don't know what that means. If you like, I can search the web for, I wanted to highlight his results can only be considered as scientific if they have survived the scrutiny of experts. This is the basis of the peer review of research articles, a process to which all scientists know they had to submit themselves.
I don't know what happened, but
sounds like Siri kicking in.
Okay, so this is why let me go on then. How does the process go? a negative opinion on an article must be accompanied by an analysis of why a critical view is expressed. Then the author is given the opportunity to reply to the challenge. Published articles in high-quality journals are published after having successfully passed this critical step. This is one dimension of the culture of doubt. You need to convince others of the soundness of your statements in a contradictory exchange, and such a process of paramount importance to give value to scientific results. I want to recall here a very good example of another exercise of doubt, and this one at the highest level. On the 12th of June, 1913, the Prussian Academy of Sciences issued a statement offering a position to Albert Einstein in Berlin. Of course, the basis for the appointment was the extraordinary contributions he made earlier in the century, in particular in the year 1905, with 4 publications that revolutionized science. One of them proposed as explanation of the photoelectric effect, suggesting the quantum nature of light. Concerning this claim, the statement of the Prussian Academy says, so I read it in German and translate immediately afterwards. Dass in seinen Spekulationen gelegentlich nur einmal über das Ziel hinausgeschossen haben mag, wie zum Beispiel in seiner Hypothese der Lichtquanten, wird man ihm nicht allzu schwer anrechnen dürfen. So, rough translation, the fact that in his speculation, he may have gone a bit too far. Example in his statement about the quantum nature of light, we should not really take that too badly on him. But also what is very important, and of course, what is very important that the 4 signatories of the statement were Max Planck, Walter Nernst, Heinrich Rubens, and Ernst Warburg. And the first 2 were Nobel Prize winners at that time. An explicit doubt put in writing 8 years after the publication, but it is critical to mention that the sentence I just read is followed by another one. And then I won't read the German version, I will just give you the translation. But one should remember that to dare to take risk is really something which allows in the most exact sciences the possibility of having true new things happening. Therefore, doubt is absolutely legitimate, but one must permanently keep an open mind. It just shows that bringing the new ideas that challenge beliefs creates resistance, not only from religious circles, but from the scientific community itself, also among the most prominent members. Such a fact must always be kept in mind. This is why it is so important to accept that researchers take risk. I'm coming to my 4th point. Especially in recent years, the role of statistical data to analyze phenomena, in particular complex ones, has grown considerably. They are, for example, at the heart of the new paradigm on which artificial intelligence is based today. While using such tools, the main challenge is to identify patterns within the data. In many respects, this gives the push to develop a new science, data science, for development of which new mathematical approaches are of critical importance. This has become possible through a combination of new tools that became available. Some are theoretical, such as remote sensing that allows to select data in a decentralized way. Some are computational, since the new extraordinary power acquired by computers makes it possible to handle huge amounts of data. Still, a lot of attention has to be dedicated to avoid being caught by artifacts. This requires also that a much wider community be exposed to dealing with statistics, a domain that has been present in the running of society for a long time, but not in a way that has the potential of touching directly are individual behaviors, hence the growing importance of statistical literacy. The same applies to simulations. A key tool today for a number of domains, in particular those having to do with climate change, to study the possible evolution of such an immensely complex system requires to have access in a rather uniform way to physical data covering the whole globe. For that, one needs to develop scenarios based on different hypotheses. Some have to do with the impact over the years of proposed measures. Some have to do with new phenomena that still need to be explored. For example, the liberation of methane due to the warming of regions such as Siberia that used to remain frozen. The only possibility to navigate between these scenarios is frequent updates based on the new data available, a huge effort that can only be done in a good way through the implication of global networks of scientists having developed standards and patterns of collaboration. The fifth topic I want to touch, actually, I already touched the issue of time needed by researchers to guarantee that the results produced are appropriately certified. This is, of course, only one aspect through which time is of the essence. The other is that the scientific approach doesn't ensure that the research project is going to be completed on time. The main point here is, of course, that even if a strategy to deal with the problem has been elaborated, one never knows whether it will be successful until the process has been completed. Research is about understanding processes one really doesn't know. This leads me to a phenomenon that is often poorly understood and therefore not easily accepted, namely the importance of serendipity in the conduct of research. The name itself sounds mysterious, and it is in some way, since it is based on an epic telling the story of the three sons of a king of Sri Lanka, written by the Persian poet Amir Khusrau in 1302. The name Serendib was the Persian name of the country at the time. The name was forged by Horace Walpole and can be found in a letter dated 1754. More attention was given to it by Robert Merton in his article Sociological Theory, published in 1945. Serendipity refers to the fact that, I'm quoting the definition by Merton, some major discoveries did happen while looking at a very different problem by luck or sagacity. A well-publicized example of such a situation is the discovery of penicillin after the unintentional contamination of a culture. The importance of serendipity raises a key issue. How does one favor the occurrence of such happy developments? Recognizing the value of serendipity indeed challenges research programs having very rigid deliverables which do not offer enough flexibility to allow changes in the objectives pursued. This stresses the value to be given to approaches leaving scientific researchers in the lead for their work. They are indeed the ones who are in the best position of evaluating what is the most promising possible development, and in the end, the most impactful path to follow. Such a recognition is, of course, at the heart of the European Research Council and is fought for by its scientific council over and over again. To conclude the first part of the webinar, I would like to bring up two expressions that lie at the heart of my own reflection on the role of science. First, the unavoidable need to understand, and second, the irrepressible value of solidly established facts. To summarize this initial discussion on the scientific method, I would like to quote the late French astronomer André Braic, who left us too early. I'm quoting, "To understand the scientific method, one has to realize that progress comes from a continuous process of calling into question. A proposition is only scientific if it is falsifiable. In other words, if anyone can verify it or invalidate it. This is why I'm quoting again, the history of scientific ideas is an excellent school of doubt, humility, rigor, honesty, and the critical spirit, which are prime virtues in the service of a passion for knowledge. That's what I want to say in this first part. Thank you.
Wonderful. Thank you so much, Jean-Pierre, for this wonderful first part of your presentation. I already see that questions are coming in the Q&A. Feel free to upvote and we will present those to the speaker later. For now, I will invite Zoltan Dienes, who is a professor of psychology at the University of Sussex. So one of his key interests is how science works, or how it could work better. He was a pioneer in developing registered reports, a publication format whereby a publisher commits to publishing an article based on the quality of the hypothesis, regardless of whether the results confirm it or not. He was also instrumental in promoting the use of Bayesian statistical methods, which makes it possible to reason beyond the null results. And he is a dedicated supporter of green open access. Zoltan is the author of the book Understanding Psychology as a Science, published in 2008, and has recently been thinking about how to reform university governance so as to better support fundamental research. Dear Professor Dienes, thank you so much for being here, and over to you.
Thanks very much, Karen. Thanks to Jean-Pierre for a fascinating 20 minutes. I didn't think a 20-minute tour of philosophy of science would be so interesting. One thing you highlighted there was the accumulation of facts, and what was sort of lurking in the background a bit is theory testing. And I was wondering what you thought about the balance between those two. I mean, theories came in terms of concepts. Concept of temperature depends on the theory or energy. Though science is more than just the accumulation of facts. And one part of it is natural history, you could say, and another part is theory testing. And I think in psychology, what a lot of psychologists do is sort of natural history, while framing it as theory testing. And the question is, what's to be done about that? And so one view is that it should be more openly just natural history. I wonder what would happen if we did this and we collect some facts. The other view is it should do the theory testing more properly, which is my view, which is incidentally part of my interest in registered reports, which is most of the time about testing theories, making sure you've set up conditions which are agreed by reviewers and editors and author jointly before you run the experiment, to make sure that results could count against the theory as much as count for it. So I know there's sort of been a bit of debate about the relative balance of natural history and theory testing in different areas. I wondered if it was sort of theory testing was backgrounded in your account just now, sort of deliberately, or if you just wanted to highlight certain other things, particularly in this age of pseudo-facts. It seemed important to you to focus on severely testing facts as such and being critical about facts.
Well, first of all, I'm a mathematician, so I'm really at one end of the spectrum. And from that point of view, as a mathematician, if I look at how the discipline developed over the centuries, definitely until some kind of a framework was developed to do things, things couldn't be done. And for example, of course, example mathematicians take all the time has to do with the history of numbers. looks like numbers is something very simple, and actually basically all cultures have developed the notion of numbers. But if you look now at the level of sophistications that numbers have taken, and the number of hidden things which are in numbers, look at everything, all the efforts going into understanding prime numbers, for example, is quite remarkable. So as a mathematician, just to conclude on this, of course, without having a setting, of course, it's very difficult to move forward in science. Actually, one should also stress at the same time, and I'm sure you're aware of this, that some beliefs, and in particular, including by the most brilliant mathematicians like David Hilbert, who believe that actually anything which could be developed formally could actually be in the end proven. And of course, this has been proved to be wrong. And actually, so it was clear that some belief that if you go to a certain level of formality, things can be done. It's clear now that mathematicians have to be very, very careful with the kind of axioms they build their work on. So now, if you move on to other fields, which of course is the purpose of your question, of course, for me, in a sense, facts need some kind of a framework, and the framework necessarily is a theoretical framework. So I think the balance or the equilibrium between the two is very, very important. And actually, even some extraordinary experimental achievement, like the experiment in CERN about the LHC, about the Higgs boson, itself needs to be commented, and actually it was commented a lot, because the recording of data has been so massive that actually even the extraordinary tools that they have to deal with the data, some data had to be discarded. And how do you discard some of the data? Well, you discard some of the data on the basis of some theoretical prescription. So in a sense, as you said, your job is to challenge theories, but how can you judge an experiment for which already some of the data have been discarded on the basis of a theoretical assumption? And I fully understand why it was done, and I'm not saying it was foolish, because it was done, of course, very carefully. But still, you see that that's a good example. We're keeping a balance between data and actually experimental facts, you can say, and really using these facts to develop further and challenge a theory is clearly put in a very sharp light. Of course, if you go to other complex systems, for example, for typical cases is of course what has to do with climate change. You know, the collection of data is so complicated, and then you have the challenge of time, because in a sense you have recorded data for a certain period of time, but at the if you want to compare with the scale at which you want to do things, are you sure that the 30 years, 50 years that you have recorded, and of course you can get, when I say this, it's really data which had been recorded in a kind of homogeneous way, but of course you can go back further and get data recorded in a different way. Are you sure it's enough to really anticipate what would be the evolution? And again, for another very complex system, which is the way the cells function and everything which has to do with the biology, the complexity of the human genome and even smaller structures is so big that, and you know that the things which matter are not just the components, but how they are organized in 3 dimensions. And so you see, that's the present challenge for science. That is, we know that we have now to deal with complex systems. There is no way we can avoid that. and therefore we have to be very careful and very, very meticulous in the way we, as you said, balance theoretical knowledge and experimental data. Yeah. So this is really something fundamental for the future, and for which I'm not sure we are training our students properly in this respect.
Yeah, I think this is a beautiful end of this first part. Thank you so much, Professor DNS, and thank you, Jean-Pierre, for the answer. And we will now let Professor Bourguignon to present the second part of the seminar. So if you're ready for it, over to you again, Jean-Pierre.
Thank you very much. I'm indeed ready. So in this part, why it matters, second part of the title, I would like to consider relations between four communities. The scientific communities, and I'm using the plural on purpose, the community of policymakers, in particular politicians, the media, with a special attention to journalists, and the general public. I want to do this having in mind some features of the points I highlighted in the first part concerning the scientific method. Some can become, or even are, in my opinion, obstacles, or at least points necessitating further efforts for the development of sound relations between these four communities. To start with, I will list three of them, of these critical points. The first one is the invisibility of the efforts required by scientific research to be successful. Of course, invisibility is a bit strong, but let me use this word. Second point, the speed at which radical new achievements are considered matter of fact. And third, the illusion that to give orders to researchers and to list deliverables is the right approach, negating the value of freedom of research. So these were the 3 points I wanted to highlight and look at the relations between the communities concerning these points. It goes without saying that for me, the challenge posed by active fake news propagators generates a real threat for the long-term credibility of the scientific community vis-à-vis several other communities. We must always have this in mind, in the back of our mind, and actually this may be a point on which we have in the short term to concentrate our efforts. Through this part, I will be using the situation created by the pandemic as a revelator of the problems. Although some people have been warning such a health threat may happen, and some prior events showed such a possibility did exist, the speed at which the pandemic spread and the global extent it took were truly overwhelming. Therefore, calls for action came so rapidly that it was difficult for scientists to take some distance with what was happening and to organize a collective action with a more strategic view. Indeed, many of them were busy taking new initiatives to deal with the pandemic itself or with the efforts that the initial lockdown created in terms of teaching, interactions with students, management of lab, as well as responding to pressing requests for expression in the media. Let me first review some typical features of the four communities I listed that need to be taken into consideration, in my opinion, in order to discuss their relations appropriately. Starting with the scientific communities, one can say that although, as is well known, scientific research is fantastically diverse in the way it is performed, scientists are highly conscious of the value of the scientific method and of the constraints it puts on them in terms of rigor, carefulness, humility, and honesty. This being said, exerting the critical spirit, as André Braic put it, in the special circumstances created by the pandemic was difficult because of possible misuse by other actors of critical arguments put forward. Policymakers exert responsibilities and therefore need to take into consideration the mandates they have received, either from the organization they work for or from the people who elected them. For them, the time of the pandemic was very special in that it required quick decisions because the situation didn't allow for inaction in view of the potentially great damages. Several of them enhanced procedures to receive regular advice from scientists. Actually, the grave consequences the absence in some countries of such close exchanges had on the efficiency of policies implemented became soon apparent. Special task forces were put in place and funding made available to support targeted research in many institutions. Still, a fact that has a direct bearing on the issue we want to tackle is the general lack of acculturation with scientific facts and processes of many politicians. For the media too, the period was very challenging because of the high expectations from their audiences in terms of rapidity of information. This was done sometimes at the expense of accuracy, in particular on issues where no well-proven facts were available. Soon came the further challenge of non-repeating oneself when the situation continued to be critical. For sure, journalists who had over time established trustworthy relations with scientists had an advantage. But what could they do when confronted with a situation where their regular correspondent remained on the reserve? One has to wait and see whether the type of relation that developed through the critical period of the pandemic will have a long-term effect on the level of contacts of the media community with scientists. It is difficult to speak of the relations of scientists with the general public, as it is such an inhomogeneous group. For example, one has to distinguish between people who are relying intensely on social media for their information and others. The exposure to contradictory information is, of course, very different. What makes also an important difference is the background education that people have received and their level of interest in scientific issues that they have developed. It is therefore likely that a uniform approach towards the general public in terms of their appreciation of the scientific method is not going to work. This means that the panoply of tools targeting different groups will have to be developed, in particular to address the issues I now would like to review. So I'm coming to the 3 points I made. Concerning efforts required by scientific research to be successful, the different communities I chose to discuss have variable opportunities to appreciate them. Policymakers are regularly confronted with requests to give enough means to support research coming from scientific communities, and in some countries from industry representatives. Many politicians, since they are the ones deciding on the money, are tempted to tell researchers what to do with the money, pushing forward and often imposing short-term agendas. In the context of the pandemic, this was understandable, since likely citizens will judge them on results achieved by the measures taken. Of course, as scientists, we know this is not an optimal strategy because of the time needed to achieve results and the high value understanding natural mechanisms in depth should receive, as pointed earlier. The pandemic provided a fantastic example of the value of trust in scientists and of long-term investments. Development of mRNA vaccines to deal with COVID-19 was only possible because this route had been explored for quite some time. And also the technology to transform the knowledge about the boost RNA could give to immunity into a vaccine. Very eloquently, in the first webinar organized by the association, Hugo Chahine explained the long route that needed to be traveled to achieve both. such an exceptionally quick production of a key solution to the global threat was the result of the vision of some researchers and the long-term investment some institutions made in them. I was, of course, pleased to see that the ERC was one of them. Still, not so many policymakers have recognized this fact. Therefore, we must keep explaining what made this extraordinary success possible. Good quality media people are willing to present illustrative stories of successful scientists who so often tell how tortuous their path to reach the light was. Still, most of the time, for journalists, what counts is to tell successful stories as early as possible to win the race with their competitors from other media, without paying much attention to conditions that made the success possible. And we know behind a scientific success, there are always people, and very often too, the trust they won from colleagues and institutions played the key role. With the general public, on the matter of appreciating how much efforts went into obtaining a scientific result, the issue is that too often, the time they can dedicate to learn about the story is too short to understand properly the process that made the success possible. Another element to be appreciated is the dedication it took from the scientists. This is where we touch the issue of the quality of the information available and of the conditions needed to have it ring bells in people's mind. This depends heavily on the early exposure to how science works. This gives me a good transition to my second point. Since a few years, we are subject to a deluge of information. Any new piece is immediately replaced by another piece. In this way, radical new achievements are quickly considered routine and become old stuff very rapidly. Historic depth is therefore easily lost. This is why teaching a clear view of the historic steps that transform science is so important. This is the more important that the 20th century has brought so many radical changes to our understanding of the world. Typical example is provided by scales that could be visualized thanks to the development of new sophisticated instruments. They open access to completely new phenomena and enable experiments that were not conceivable before. Actually, once more, the pandemic provides us with superb examples of the acceleration of scientific history. Recall that the double helix structure of the DNA was proposed in 1953 by Francis H. Crick and James D. Watson. Then the full sequencing of the human genome was achieved only in 2003, after a more than 10 years completely international multi-billion dollars effort. The sequencing of the coronavirus responsible for the pandemic was done in a matter of weeks in China and shared worldwide immediately. But the story doesn't stop there. Since then, billions of tests to detect the presence of the virus in people's body have been performed in all countries in labs often around the corner. Even more spectacular, there is now a widespread capacity to detect precisely in which way variants of the virus differ from the original one. And all this is happening at the nanometer scale. That is, remember, a billionth of a meter. The blurring of the historic perspective goes along with the belief that the capacity of scientific research has no limit. Scientists can be asked to solve almost instantaneously any problem that appears. This is, of course, misleading, and it affects the relation with the general public, for whom, for example, the incredible effort that sequencing the human genome represented is not perceived, when it happened not even 20 years ago. When the Human Genome Project was launched, there were competent people, doubting of its feasibility because of the huge complexity of data to be identified and assembled. From this point of view, most media do not help, caught as they are in keeping the deluge of information flow. The matter is a bit different for policymakers who are necessarily aware of what needs to come next, hence where the front of knowledge lies. It leads me to discuss further how to take into account the reality of the process by which new knowledge can be created. That's my third point. The plea made almost constantly by scientists to having the freedom of setting their research objectives is often not met with success. In a number of countries, policymakers insist on setting the agenda and on fixing the listed variables to be produced in exchange of support. There are several dimensions to this question. The first one is, of course, the illusion that if one objective is set, it will be achieved, as if research is a sure thing where we can order results as in a menu. The second is that, without any depth understanding of basic phenomena, there is no hope to actually solve some problems. The story behind the mRNA vaccines is there to remind us of this hard fact and of the value of long-term perspectives. Explaining why freedom is so important in the setting of research policies is not so easy when one has to do it for the media or the general public. Indeed, such a plea is often perceived as an abusive demand by researchers, since after all, most of the money it means, since most of the time, it means spending public money. It is in this context that having a better perception of the important role played by serendipity would be very useful. As explained earlier, the research process works through a mix of theoretical progress and experimental verification of hypotheses put forward, but also thanks to serendipity. We should not miss any opportunity to help people outside the scientific communities understand more deeply how the process really works. It is time for me to sum up what the situation is and why we need to make major changes in the way we scientists deal with it. The pandemic should have been an exceptional opportunity for the scientific communities to progress in getting their contributions better appreciated by the other three communities we discussed. This can be said in particular because of the decisive contribution that scientific knowledge resulting from the application of the scientific method brought to monitor and control the pandemic, even if the numerous attempts to develop an easily accessible treatment have not yet been successful. Why did we not do better? First, the scientific communities have not been able to prevent some of its members to misbehave, taking advantage of the media interest to push personal agendas. One just needs a few counterexamples to undermine trust. Second, they have not been quick enough to make available appropriate explanation of how the scientific method works. And this in relation with a number of important issues. For example, why are blind tests so important to establish whether a treatment is efficient, and why one needs time to check whether a vaccine is safe enough and efficient? There is the needs of 3 phases of clinical trials to develop sound statistics, or else how epidemiological models functions, a good example of the use of simulations, as well as the importance of understanding exponential growth. Third, how is it possible that we have not been able to prevent a mistrust of vaccine to spread so widely on the basis of all kinds of misleading theories, some of them truly crazy? Having permanent access to updated data with the real figures relevant for your area and your age group would have been a step in the right direction. But I don't think this was taken care of by some decentralized scientific organization. I also believe that not enough research has been conducted on the epidemic, quote unquote, of refusals to vaccine. Actually, this is precisely what Professor Francis Collins, who led the National Institutes of Health, NIH, for more than 10 years, said about misinformation in conclusion of the retirement interview he gave to Science. I quote him: "This has turned out to be a much more severe situation than I would have imagined a year ago. I wish we had more insights from behavioral social science research into how this come to pass and why it could have gotten so completely widespread. That's another epidemic that is not going to go away, even if we triumph over COVID-19. End of quote. Later in the same paragraph, he also says, I'm quoting again, in many instances, we seem to have lost a sense of how to tell the difference between a fact and an opinion, or some Facebook post that's frankly a lie. That's truly dangerous. End of quote. My conclusion, we scientists have an urgent task to take up, namely improving in a radical way our relation with other communities at large. This can only happen through a massive effort to publicize the scientific method. And this must start very early in schools. In many countries, France is one of them, this requires a rather radical transformation on the way teachers are trained. Understanding the method is essential to consolidate the knowledge. Thank you.
Thank you. Thank you, Jean-Pierre. Again, for this very engaging talk that concludes your presentation. I'm now very pleased to welcome Dr. Véronique Allouin, who is the Secretary General of the Belgian Fund for Scientific Research, the funding agency of the French-speaking part of Belgium, as well as the president of the European Science Foundation, Science Connect. Dr. Allouin's background is chemical engineering, which she studied at the Université Libre de Bruxelles. She became a full professor there in 2000, leading the chemical engineering group until 2008, and later acted as a president of the School of Bioengineering and as vice rector of research and development. She's also a member of the General Assembly of Science Europe and of the Global Science Forum. So, Dr. Allouin, we are very pleased to invite you to share your thoughts about Jean-Pierre's presentation. We have to be concise and short, also in the questions and answers. Please take the floor.
Thank you very much. Thank you, Jean-Pierre. I didn't see the time pass at all. It was very clear communication on an important subject, which is the need to explain the scientific method to the general public and to the policymakers, in particular, to try to limit the often devastating impact of social networks with the manipulations they allow. Indeed, I share with you that we can only regret that the opportunity offered by the pandemic crisis was not taken to communicate widely on the scientific method. But generally speaking, the framework is in fact very broad, much broader than the pandemic context we are experiencing now. I think it's about trust or distrust in science and its outputs, about trust or distrust in scientists, and trust or distrust in institutions. And I think it's an excellent idea to also communicate on the scientific method and not only on science results. Indeed, there has been an increasing amount of popularization of science in recent decades, but science is difficult. You told it also. Science is difficult, and it's difficult to promote something difficult without major simplifications. And as a consequence, part of the general public believes that science is not so difficult, is not aware of the necessary prerequisites, and feel entitled to post his or her opinions on social networks without critical thinking. And you are right when you pointed out two interfaces where you believe we need to make considerable progress, the political world and the general public. And I think that in this respect, research funding agencies have a role to play. And for example, I've noticed that the Swiss National Fund for Research has launched 10 years ago a funding instrument, Agora, that aims to foster dialogue between scientists and society. It funds projects having a duration of up to 3 years and a budget of up to 200,000 Swiss francs. But very important, in line with the principles of the Dora Declaration, Agora projects are considered scientific outputs. The SNFRS, the National Fund, Swiss National Fund, therefore, takes them into account when evaluating the scientific track record of a researcher. And those projects also address an audience that is not specialized in the communicated topics, general public, but also a smaller target audience with, who play a pivotal role in society, such as politicians. So I actually have two questions. As I mentioned, as the vast effort to popularize science, efforts to make science attractive, the hyper-availability of a whole series of scientific publications caused, in a way, science to lose its status and its very essence, which is marked by exigency, nuance, complexity, and difficulty. And that there is therefore a perverse effect. And my second question is, everyone must take their share of responsibility and initiative in this pedagogy and communication of the scientific method. So what would be your concrete advice in this respect to funding institutions such as the FNRS? And do you think, for instance, that an initiative such as the Agora Swiss one would at least partially address the problem and should be generalized in the research funding agencies? Thank you.
Thank you, Veronique, for your question, and also remembering that efforts for popularization of science have really flourished in the last years. Maybe two comments for me, because in a sense, one thing which why did I talk a lot about the method? And of course, the popularization of science very often is focused on results, and actually not so much on the method itself. And well, because I think if you really, that was my last sentence of conclusion, if you really want people to get passionate about science, and that's what we need them to really expect this as to measure the, to look at science with something exciting, in particularly young children. Because we want a number of them to become scientists. I think it's very important that they could see that even at their level, by applying some, typically the scientific method, then they can really gain a knowledge which has a different value than just something you just learn by heart. And it's true that many systems, friends, from that point of view, maybe even extreme, put a lot of emphasis on the fact that people should know things. Mm-hmm. When actually, of course, it's important to know some things. Without knowing anything, you cannot do anything. But if you really want to be sure that you have understood, as soon as you have understood something, you just cannot forget it. I like very much a quote from Évariste Galois, who said that to make of understanding a substitute to memory. Because if you have really understood something deeply, you cannot forget it. And so I think this is this combination of having personal direct access to some phenomena for which you derive your own strategy, and then you understand that you can actually prove something. And of course, what you have proven then is something you are going to keep. So this balance in education between, of course, being exposed to things which have been found by others, but things that you can also, in a sense, become familiar with because you derive them yourself, looks to me very important. So to conclude, my point is to say, not to say that popularization was a bad thing, not at all, but I think we probably have to think a bit more about why is this method help us to conclude what we have concluded, and not just the conclusion. So the process as much as the conclusion. That would be my reaction to your question.
Thank you. Thank you both. Thank you, Dr. Alain and Jean-Pierre for the answer. Time-wise, we have to move on now, and I would like to invite our final panelist, Christian de Brul. Christian de Brul is a Belgian science journalist who spent most of his career at the newspaper Le Soir in Brussels, where he was in charge of the health and science section. And in 2013, he took an active part in the launch of Horizon, which is the EU research and innovation magazine. And in 2014, he launched an online web media in Belgium called dailyscience.be, which proposes daily information about science, research, and innovation conducted in Belgium or involving Belgian researchers. Christian also keeps an eye on what is going on in science and research at the European and international level. Christian, over to you.
Thank you very much, and thank you, Jean-Pierre, for your presentation and all the questions that have been asked until now. My small contribution to this webinar is related to the presence of scientists, of researchers themselves in the communication process. And well, we are here all convinced about the value of science and research. We are also convinced about the importance of sharing with the public, with politicians, with journalists, maybe also, well, advances in science, but also reflection on science, or how science is done, how science is conducted, funded, and so on. And well, we are here, maybe 100 or 200 people attending this webinar, maybe more, I don't have the exact figures. But we are not the only one convinced of all these matters. If you turn back to the last Eurobarometer related to science that was published this year and conducted this year, you can see that 86% of the European citizens are having quite a positive attitude towards science and technology. They think it's positive for their own life and for society, which is a very good point. If you go into the details, in one detail of the Eurobarometer related to the scientist and the perception of the scientist by the general public, the very first characteristic that is mentioned by a lot of citizens, it's that scientists are intelligent people, which is also good news indeed for all of the scientists. A little more than half of the respondents also say that the scientists are reliable people in whatever they are doing, and another adjective given is also collaborative. Now, if I go to the very bottom of the scale, there are some bad sides related to the perception of scientists by the public. And one of these negative characteristics is, and I'm just reading part of this Eurobarometer, the most commonly negative characteristic associated with scientists is bad at communicating. And this is really key, of course, if you want to improve the perception of science. As far as science, if you consider science as, well, something producing results and new information and so on, but also if you consider the way you have been speaking about the methodology of science, how does science work? And I believe, well, a part of the responsibility to make this well understood or better understood by the public is probably, well, to rely more on the scientists themselves. And here is my question then, Jean-Pierre, to you. Shouldn't public bodies funding research at whatever level it might be should make the scientists more aware of their responsibility regarding the communication about science, and shouldn't they be obliged in some ways to dedicate part of the public funding, public money they receive to initiate, well, communication activities? Intelligent, since these are very bright people, 86% of the European citizens say so, but intelligent way of communicating their results or their methodology, maybe not just through just a website or a small video on YouTube, for instance.
Well, thank you, Christian, for the question and for also your contribution to dealing with the issue I'm trying to tackle. Actually, 2 points. First of all, we know that among scientists, there are people who are good communicators and people not so good communicators. So for sure, we should help the ones who have both the talent, but also the willingness to participate in in more communication. We should help them to become more professional. And I'm sure that people who can play a role in this are people like you. That is because you are a professional of communication. So I think we should do more efforts. But the idea that it becomes an obligation, I'm not sure it's going to work that way. For sure, having incentives or having people helped in their efforts to communicate more, I'm talking about scientists, is certainly something which needs to be considered. And as you know, I mean, even if I'm quoting ERC, ERC is making a lot of effort for this, and this is one of the few programs of the European Research Commission, which has really a communication unit, and actually very high quality communication unit. So in particular, one thing we did, which had a great success, was the so-called ERC Comics, which was an attempt to use other tools to get ERC grantees to communicate about their work. So my answer to your question is, for sure, we need to improve on this, and therefore rely and help and accompany people who definitely have both the willingness and the talent to do it. And definitely the key point is also to really be sure that we are not missing some absolutely critical public. And one critical public I was mentioning in passing in my speech was in particular the primary school teachers, because I think one of the critical elements is to get young kids, and of course people who teach them, comfortable with the idea of being confronted with this science. And I must say, for the moment, in a number of countries, this is not the case. So I think we should be sure that when we choose our targets, there should be a number of different targets. And of course, as usual, when there are different targets, the tools to do that should be different. For example, if you look at the situation in France for professeurs des écoles, people teaching in primary schools, many of them are people who, in their own personal history, they were confronted negatively with science. So, of course, when they approach even the very elementary mathematics or physics or sciences naturelles, as we tend to call them, they have some kind of a very awkward position because themselves are not comfortable with it. So I think we need to make an effort because, of course, these people are not stupid at all. So we should be able to make them still potential ambassadors of the scientific method. But for the moment, this effort is not happening. And of course, there are counterexamples. I'm not saying everybody is like this, but so you see, in making the effort you are suggesting, I think we should also make sure that we are not missing some critical group. And one other critical group I want to single out is, of course, politicians, because I think there are very few opportunities to have politicians being confronted with scientists really in a, I would say, in a leisurely way, which of course doesn't happen often for the life politicians, which tend to be over occupied. But I think we have to create instances where these possibilities exist. In the European Parliament, for example, there is this so-called STOA, which is the Science Technology Options Assessment, where definitely a number of members of Parliament accept to meet not only scientists, but also people from experts in technology. In the French system, we have the so-called OPEX, which is Office Parlementaire pour l'évaluation des choix scientifiques et technologiques. And so these people who are elected people accept to spend some of their energy listening to scientists, listening to experts, and asking them questions. And I must say that we must have such processes much more widely distributed, but also maybe even the content of the exchange made available, which for the moment tends to be a very technical document when it should be a document which should be made available much more widely. And I know in France, Cédric Villani, who has been chairing the OPEX, is really trying to make such efforts, which of course require energy, dedication, means, and so on. and even maybe a change of a culture. So I think
like a wonderful effort. Yeah.
Sorry for being too long.
No, yeah, sounds great. Yeah, we could go on forever. I know there's so much to say about this. Thank you so much, Christian. Thank you, Jean-Pierre, for the answer. So I would love to also give the opportunity. So Simon will take over for the audience to see if there is a question from the audience that was voted up. Simon, floor's yours.
Yeah, thank you very much, Karine. Thank you very much, Jean-Pierre, for these two fantastic lectures, reminding us very fundamental principle of what we should do, how we should work and improve our work. So I will ask one or two questions from the audience according to ranking by voting. So the first question or the first comment on question is from Michael Bojdis. I hope I'm saying your name appropriately, who mentioned that in May 2021, he had asked Olaf Scholz, who is now Chancellor of Germany, how could it be possible to lobby that EU member states spend 3% of their gross product for research and development? And the answers was not fully clear. Of course, it's a very complicated topic, so very difficult to answer clearly. But now the questions come to you, Jean-Pierre, as a former president of the ERC. For science to be part of policy decision-making, how can the ERC ensure that such a culture is created of engagement on scientists to be recognized and rewarded for developing the skills associated with the scientific method? So how can we do that in practice?
Well, that's a very good question. As you know, absolutely the DNA of ERC is to trust the scientists. So I think we are not going to hold the hands of scientists and tell them that they should submit projects on the scientific method. But of course, we hope that by being successful and by being bold, that is really taking risks, the ERC grantees are the fantastic ambassadors of what should be done. And of course, the issue of how much money is dedicated to research is, for me, really, it was a shock to realize that in the summer of, in July 2020, the summit of heads of states and government decided to cut Horizon Europe by more than 15%. I couldn't believe it. I mean, and at the same time claiming we must make all these transitions, climate change and digitalization and health and so on, where everybody knows that without research and innovation, there is no way we can actually reach these goals, do this transition properly. So this is this contradiction, which means that we must invent and find ways in which we can approach scientists. By the way, you know, in the US at some point, really John Holdren, who was the advisor to Barack Obama, was meeting Barack Obama typically 1 hour a week. So that was the situation in the presidency of the US. Of course, they didn't continue with Donald Trump, as you don't need a proof for that. You are sure of it in advance. But so it shows that this the natural character of these exchanges has to be developed. Of course, asking the question to the new Chancellor of Germany is kind of unfair, because Germany is above 3% of GDP spent on research. Partly because there is public money in it, also partly because the German industry is also very good in financing research. But the question should be really put to governments who have not done that. Typical example is the French government. We're still at 2.2%. Actually, partly really for good reasons, because the French industry is not so engaged in research as the German industry. So I think the public support could be better, but definitely is not so bad. But the private sector investment in France is not at the level it has in Germany, for example, or it has in Sweden, for example. So I think this is a very important question, and I think we need to bring this up. And if, you know, France at the moment is very soon in a presidential campaign, and research is totally, completely absent of any discussion on this, which makes me just, I mean, really furious. But anyway, so there is a lot of work to be done, and
that's good to hear that we need to do all this work. Now continue to work harder on the never let it go.
Yes, well, I think this is actually a beautiful end of this session. A lot of work to do still. This closes our second Science and Society event. Thank you again, Fernanda, Simon, Axel, Paulo, and the Necker Institute for handling this event. And thank you to our wonderful panelists. But most of all, thank you so much, Jean-Pierre, for sharing your experience and your science with us today. Just as a reminder, this recordings will be available on the ERC's YouTube channel. We will now close this event, but please stay tuned for more in our series of seminars, and please become members of our association if you have not yet done so, and follow us on Twitter for more news. And yeah, our account is visible, I think now. No, it isn't, but you can find it. Thank you all for the wonderful discussions, and bye-bye, everybody.
Bye-bye. Thank you very much for the invitation.
Bye.